All right, there we are. We are rolling, and let's get going. My lovely handwriting there, and all right, so I want to go through this problem here. So what we have here, this is in the Beer Vector Mechanics book. This is problem number 2.5. So you can see it in your text on page, oh, let's see, what page is that? Let me find that really quickly. That would be page 25, thank you. Page 25. So we have a stake that is a stake is being pulled out of the ground by means of two ropes as shown. Knowing that angle alpha equals 30 degrees, determine by trigonometry A, the magnitude of the force P, so that the resultant force exerted by the stake is vertical, and B, the corresponding magnitude of the resultant. So that's what we want to look at here. Sorry, I just want to, and I think we're that. Questions on that? Any questions? So, okay. So again, we have a stake here. Notice here, we have a stake here. There are essentially two forces on this. There is one known force of 120 newtons at an angle of 25 degrees from the vertical. There is another unknown force P that is being pulled at an angle alpha. And we want to know both the magnitude of P and the, basically, we know alpha as well, but we're also looking to find the magnitude of P. So essentially, we know this, and this, but we don't know P. So we're looking for P. We know this, as stated in the problem, is 30 degrees. So we know that is 30 degrees. So we could solve this a variety of ways. In fact, I might try solving this first via trigonometry, and then maybe I can solve this via what I would prefer, which would be via Cartesian methods, via rectangular form. So let's give this a shot. So let's take a look here. So what we need to know is we need to be very careful about this. We need to know that we are looking for something. This is key. The resultant force is vertical. So we're going to add these two vectors together. And when we add them together, we want the final resultant to be vertical. So let me draw out a little force triangle here. I'm going to have a vector R, a resultant vector. This resultant vector will be R. I don't yet know the magnitude of it, but I know that the resultant will be vertical. Then I'm going to have this 120 Newton force, 25 degrees from the vertical. 120 newtons at an angle of 25 degrees. Oh, gestures are a problem here. Oops, sorry, here. 25 degrees. 25 degrees, there. Then I'm going to have this force here, the force P. Now, we may be tempted to call this simply 30 degrees here, but we have to be very, very careful. See, alpha here is off of the vertical. This is alpha. So I know that this here is 30 degrees. I know this is 30 degrees. However, simply using our properties from trigonometry, or actually from geometry, alternate interior angles, I know that if this is 30 degrees, then this also has to be 30 degrees. I know that this also has to be 30 degrees. Like so. So I have a triangle now that is more like, I can actually redraw this triangle if I wish. And in fact, I will. I think that'll be, maybe that will be a bit simpler if I like. Although this is arbitrary, entirely arbitrary. This would be R. This would be 120. This would be P. This would be 25. This would be 30 degrees. And this, let's see, so this would be 55. These together would be 55. There are 180 degrees altogether in a triangle, so this would have to be 125 degrees, unless I'm really bad at math today. 125 degrees, because yeah, that will come to 180. Yes, 125 degrees. Okay, so our goal now is to find P. Now, there's a variety of different ways we could do this. I could break this up into two right triangles. I could use law of cosines. I could use any method of my choosing. But I think the easiest way to do this will be to apply the law of sines. So, if I remember the law of sines, okay, why did I choose the law of sines? Well, I like using the law of sines when I see a angle and a side across from each other that are both known. I'm looking for P, but I do know 25. So if I didn't know 25, then I wouldn't want to use the law of sines. But as long as I have one matching pair of 30 and one matching pair of side and angle, then I can use the law of sines. And okay, for those who don't remember, let me go ahead and erase this. I will draw out the law of sines really quickly, just as a brief review from trigonometry class way back in whenever it was you took it. So if I have a triangle with side lengths A, B, and C, and then angles, corresponding angles alpha, beta, and gamma, although sometimes you see this as little a and capital and lowercase a, whatever, but I always like the alpha, beta, gamma. It makes you sound smarter. So I can simply express this as A over sine alpha of alpha equals B over sine of beta equals C over sine of, oh, I cannot write today. Oh. Sine is spelled with an S, not with a C. I don't know how to spell today. Sine of gamma. And there we have the law of sines. The law of sines as laid down by some Greek dude a very long time ago. Pythagoras, Archimedes, someone. I don't know. Look it up. I'm sure you can find that out somewhere. Anyway, let's apply this beast. So actually, this one's fairly benign. The law of cosines is a bit more annoying, but this one's all right. This one's fairly easy. So now all I have to do is say the sine of 30 degrees. Actually, you know what? I could easily flip these, but because I wrote it this way, I'll put the angles on the bottom. Pen here. So I can say 120 newtons over 30 degrees is equal to P over, sine of 30 degrees, yes. Sine of 30 degrees. And yes, we'll be able to do the same sort of thing for R. P over the sine of 25 degrees. the sine of 25 degrees, like this, p over the sine of 25 degrees. And so therefore, via some simple multiplication, I can see that p is equal to 120 times the sine of 25 over the sine of 30. And I'm going to throw this into a calculator really quick, and we can get the result, the answer fairly easily. So 120 times the sine of 25 over the sine of 30. And this comes to 101.4. 101.4 newtons. Any questions on that?
What did you want to find the result from 120 and divided by sine 30 then multiplied by sine 25? Or
You could, divide this out first and then multiply it. Yes, it should give you the same answer. We could do it separately, but I just threw it all into my calculator all at once. But it depends on the complexity of your calculator. If you were working with a simple non-graphing, you might just want to do it like that, do it in separate pieces. Okay, so now basically we have the part for A. So this is the answer for A. This is the answer for A. And now we need to get the resultant R, the actual resultant, the actual vertical force that results when we pull with both of these put together. So let's do that. And I'm just going to do the same sort of thing. I'm going to say here that, well, I'm just going to extend this a little bit and say I'm going to use the same ratio and say instead of 120 over sine 30, I'm going to keep that, but I'm going to say R over the sine of 125. R over the sine of 125. Oh, we went backwards. Oh. And from this, I can then say that R is going to be equal to 120 times the sine of 125 degrees over the sine of 30 degrees. And all of this will be equal to times the sine of 125 over the sine of 30. And all of this will be equal to 196.6 newtons. Huh? Oh. 196.6 newtons. And this would be the answer for part B. So, questions on that? Okay. So, what I'm going to do here is I'm going to modify this a bit, and I want to repeat this problem, but instead using Cartesian coordinates, rectangular coordinates. So I'm going to keep my notations, make sure that's plugged in, and I'm going to actually copy the slide. So now I have another copy of it. Basically, I'll be able to post these slides online when we're done. So anyway, so let's. Oh, don't want to start. Go to. Let's see, this is still good. And let's. Okay, so I'm going to erase everything on this slide. Oh. Actually, you know what? I may not be able to erase this. I may have done goofed. Just a second. I think it actually saved those as permanent. Oh well, I can just duplicate this. Insert slide. Delete this, and I can put this right here. There. I'm going to repeat this problem now, but using Cartesian coordinates. Okay, so let's repeat this problem, but using Cartesian coordinates or using rectangular coordinates instead of using trigonometry, instead of using the triangular method. Okay, so I know that I have two forces here, and I know that I need to find a vertical resultant. So effectively, I know that R is going to be equal to, in terms of components, it's going to be equal to 0 newtons, comma, some Ry component. I know that the overall x component on this thing must be 0. I want R to have absolutely no x component whatsoever. I want it to be a purely vertical force. So if I draw a little free body diagram here, and we'll get into free body diagrams a bit more tomorrow, I'm going to have, let's see, actually let me erase that. I don't want to get into, huh? Oh, questions? What I'm saying is, okay, this is the x and y component of the resultant force. The resultant force is not going to have any. It's going to be pointing straight up. It's not going to have any horizontal component, only a vertical component. And I can use this to actually solve for the angle that or the force P that we're looking for. So let's do that. So if I have this force here, the 120, and then this thing has a 120 cosine 25, and this will have a component 120 sine 25. So that's one force. And then I'm going to have another force, force P, with components P sine 30 degrees. And this, and an x component, P cosine 30 degrees, here. And the resultant will be purely vertical. So all I'm doing here is I'm showing the two forces on the stake and their components. So force P has a horizontal component of P cosine 30 and a vertical component of P sine 30. This 120 Newton force will have an x component in the negative x direction of 120 times the cosine of 25 degrees and a vertical component of 120 times the sine of 25 degrees. So, any questions on how I set that up? If you have any questions, feel free to ask at any time. So, what I can say now is, okay, we said earlier that R has components Rx and Ry, and I know in this case that Rx is 0. The x component of R is 0. However, this is also equal to the sum of the x components of each of the two forces. The x component of the resultant force is equal to the summation of the x component of each of the individual forces. So I can say that this is going to be equal to, I don't like that. This is going to be equal to, now notice now in terms of which one I call A and which one I call B, it doesn't matter. It's totally arbitrary. It does not matter one bit whatsoever. This is commutative. You can add them in any order whatsoever. One property of vector addition is that it's commutative. You can add them A first, B first, C first, D first. It doesn't matter. If you do it right, you'll get the same result. So here, AX is going to be, now we got to be very careful with this. I don't just want to say 120 cosine 25. I want to say negative 120 cosine 25 degrees. Do pay very close attention to that. This is negative. That is important. This is negative because this thing is pointing in the negative x direction. This is negative because it's pointing in the negative x direction. And, oh my goodness, I am stupid. Do you see the problem? I made a very, 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 very big problem. What did I do wrong? What about the angle? See, look here. I was on autopilot, and I'm so used to saying that the horizontal component is the cosine. Look what I did. Oh man, exactly. So I need to switch these. So, contrary to popular opinion, I am not infallible. So let's just fix. I'll just fix that here, and it'll be like it never happened. Oh, I don't know. I don't know what you're talking about. This was always 120 sine of 25 degrees. This was always 120 cosine of 25 degrees. Pay no attention to the man behind the curtain. Anyway, okay. So there are two ways I could do that. I could make this sine and this cosine, or I could actually go and use the angle of 65 degrees here, the angle from the horizontal. Either one would be perfectly acceptable. So I need to destroy the evidence here and do that. So negative 120 sine of 25 degrees. My brain's still on summer break. And this will be plus cosine. And look what I did. Did the same thing here. Oh well. Such is life. That was a test. That's all it was. Just make sure if you're paying attention. That's all it was. Yeah, that's what we'll go with. Sine and cosine of 30 degrees. And pointer options, eraser, there we go. And sine of 30 degrees equals 0. And if you work through the math on this, you will find that P is equal to 120 sine 25 over the sine of 30 degrees, which is exactly what we had before, I believe. Yes, it is. And we will, of course, get 101.4 newtons. 101.4 newtons. And that's the answer for part A. All right, and then the resultant. Well, let's see. R is basically Ry. So if we get R is essentially just Ry here, because there is no Rx. In this case, it's going to be, let's see, it's just going to simply be AY plus BY, which will be 120 times the cosine of 25 degrees, right? Plus 101.4 times the cosine of 30 degrees. Again, all this is P cosine 30 degrees. Again, as a reminder, the reason we're doing cosine on the vertical and sine on the horizontal for this one is because our angles are defined from the vertical. If you're used to, now usually you're used to seeing the angle off the horizontal, and so it's very easy to get caught in the trap that I just got caught in, where you say, oh, x component, oh, that's cosine, oh, that's y component, that's sine, just like that. But in reality, you do need to be paying a bit more attention, which I clearly wasn't, and realize that you need to be mindful of where the angle is being taken off of. So let's throw that in a calculator, and we will get, hopefully we'll get the same answer if we're doing this correctly. Plus 101.4 times the cosine 30, and we do indeed get the correct answer of 196.6 newtons. And that is the answer for part B. All right, so any questions on that? Hopefully that's a fairly straightforward example of finding, of doing two-dimensional vector addition.
On exams, how strict are you about putting units on every intermediate step?
Units on every intermediate step. Let's see how strict I am on that. I want to at least make sure your final answer has a unit on it. So do make sure your final answer at least has a unit on it. Sometimes you'll notice sometimes I leave units off here, but generally I want to have the unit. I at least try to put my unit in the final answer. So if I was being very strict and very proper, I'd put the unit at every stage along the way. But I realize on some long form problems it gets very tedious to write the units out every step along the way. So if you want to be very proper, yes, you can put the units each and every step, but just at least make sure you have the final unit in the final answer. So, okay. Let's see. Any other questions about this? Okay. All right, so moving along, I would just like to demonstrate another one here, finding the x and y components of the forces shown here. So, what do we have here? What is this? Anyone know what this is? What I mean by this? I mean, what is this object? Huh? It's not a hinge, no. Well, maybe. I guess it could be a hinge. But when I see that, I see a pad-eye. You all know what a pad-eye is? A pad-eye is a device. It's shaped like that. It's just a lug of metal. It's used for lifting. I've designed a fair number of these when working in the offshore industry. We would design these to lift various pieces of equipment, lift various arrangements of equipment, various sort of pads and things like that with big heavy weights. And we design these things. You might design these things to. These could be. You have all sorts of different versions of this, from things that are very small, that hold a couple hundred pounds, to things that hold dozens of tons. You can have 100-ton pad-eye for incredibly high loads, things like that. But anyway, all this is now, I guess, if this was a cross-sectional view, this probably could be a hinge, actually, in certain applications. But so I guess maybe it's just one of those eye of the beholder type things. It doesn't actually state what this is. But when I see this, I see a pad-eye, but I guess it could be a hinge as well. But anyway, whatever this thing is, I'm going to call it a pad-eye because I think it looks like a pad-eye, but whatever. There are a variety of forces acting through the center of this. And what we want to do is we want to find the x and y components of each force. And you know what? I'm going to modify this a bit and say, and the resultant. Let's modify this a bit. Of all forces. Of all forces applied. And the resultant of all forces applied. So I'm going to call this one force A, this one force B, and this one force C. Can you all read the numbers on here on the back? Can you all read that? Okay, good. Okay, so let's see here. So what I'm going to do is, first I'm going to break this down into each of these forces down into its x and y components. Then I'm simply going to add them up. And we'll look at that. Let's see. So let's work through this. So vector A is going to be equal to, I'm going to do this in vector notation. Oh, I screwed up. Okay. Let's say negative 150 newtons times the cosine of 35 degrees, comma, 150 newtons times the sine of 35 degrees. So that will come to a certain set of numbers. Let me get that really quickly. So, negative 150 times the cosine of 35, comma, 150 sine of 35. 150 cosine 35, 150 sine of 35. And what this comes to is, this comes to negative 122 newtons, or negative 122.8 newtons, comma, 86.0 newtons. So this has an x component of negative 122.8 and a y component of 86.0. I could also express this, if I was so inclined, as negative 122.8 newtons I plus 86.0 newtons J. Either of these are perfectly valid. Usually I write my rectangular vectors in this form simply because it's a bit more condensed than the I and J. I don't have to write it with the addition sign and all that other stuff, but it's purely a style choice. Means exactly the same thing. Vector B, now I'm going to take extra special care this time to take the angle off of the x-axis. So B will have, note I did make the x component of A negative because it's pointing in the negative x direction. So B here is going to have an angle of 70 degrees taken off of the x-axis. So this is 120 newtons times the cosine of 70 degrees, comma, 120 newtons times the sine of 70 degrees. All right, let's run through that. 120 cosine 70 and 120 sine 70. And this comes to 41.04 newtons, comma, 112.8 newtons, like so. And then finally C, vector C, is going to be 80 newtons cosine 40, comma, 80 newtons sine 40. Now in this class we typically deal with angles and degrees, but if you were so inclined, you could do all of this in radians like you do in calculus class, but we usually deal with degrees in this class. All right. And so this is going to come to 80 cosine 40, comma, 80 sine 40. And that would be 61.28 newtons I and 51.42 newtons J. Like so. So what I now have here, are the x and y components of each of the three vectors. So I have the x and y components of A, the x and y components of B, and the x and y components of C. So any questions so far on how I got this? Hopefully it's fairly straightforward. Tomorrow it'll get a bit more complicated when we deal with the three-dimensional stuff, and I imagine there'll be a few more questions there. But today we're sticking with the fairly straightforward two-dimensional things. So now I can simply say, all right, so we have actually now completed everything that the problem asked for. But now I'm taking it to the next step and finding the resultant of all the forces applied. So Rx is going to be negative 122.8 plus 41.04 plus 61.28. All right, and I'll add these up. And that's going to come to negative 20.55. And if any of you want to follow along with me as I go and check my math, feel free. I am not, as we have seen, I am not infallible, and sometimes I don't enter things in the right. Sometimes I don't enter things in the calculator properly either. But you never know. Okay, So Ry is going to be 86.0 plus 112.8 plus 51.42. Again, where I'm getting these are just the y components of each of the individual forces. And that's going to come to 250.2 newtons. So R, vector R in component form, is then equal to negative 20.5 newtons, comma, 250.2 newtons. And that's a perfectly valid way to express vector R. Now, what if I wanted to report it in polar form, though? What if I wanted to try extend this even a little bit further and get R in polar form? So let me get R in polar form. Well, let me look at where this is going to be. Yeah, it's going to be over here, basically. This is definitely exaggerated here. But I'm going to end up with a theta here, essentially, in the second quadrant. A theta in the second quadrant, and an R here. So this is just basic trig review, essentially. Theta is equal to the inverse tangent of 250. Now, I could use the negative, but I actually like just taking the angle off of the nearest x-axis and then just reporting the angle in relation to the axis, and that's what I'm going to do. But again, that's sort of a style choice. 20.5, and that comes to, let's see, inverse tangent of 250.2 over 20.55, and this comes to 85.3 degrees. And then the magnitude of R, again, if you haven't seen it before, this double bar symbol means the magnitude. So again, double bar means magnitude, is going to be equal to 20.5 squared plus 250.2 squared and the root of all that. And sorry, I'm kind of bunching my numbers together. I'm trying to fit a list in one slide. 250.2 squared plus 20.55 squared. And all of this comes to, the x component barely adds anything to the magnitude. It's about 251.0 newtons. So I could say R essentially is 251 newtons at an angle 85.3 degrees above negative x-axis. And that's how I like to express things in problems like this, above the negative x-axis. So usually when I'm writing my angles for this type of problem, I will just take the angle off of the nearest x-axis. I won't try to just you have to be very careful with the inverse tangent function. You have to be aware of where it's defined. So you do have to be very careful with that. But anyway, so that's just a review from trigonometry, really. So any questions on that? Yes? Oh, this? Okay, well, I was taking the angle off of the negative x-axis. So I basically set up a little triangle up here. So the question is, what happened to the negative what happened to the negative that was, the negative that was here, where did it disappear to up here? Well, when I redrew this theta, when I was taking my thetas here, like here, I was taking the angle off of the positive x-axis. But here I was taking the angle off of the negative x-axis. I was actually, by doing that, the real advantage of that is you avoid trouble with negatives. See, if you have if you just put like a negative on your, just throw a negative number into your inverse tangent function, it's going to assume it's in this quadrant. And so if I mean, what happens if I just actually do that? Let's find out. If I actually just put inverse tangent of 250.2 over negative 20.5. Oh, let me just see here. Oh, just a second. I screwed the pooch on that one. I get negative 85.3 degrees. Which, if we're taking things off of the x-axis, would actually be way down here. See the problem with that? See, if you remember from your pre-calculus days, what is the domain of the inverse tangent function? Do any of you remember that? I know I'm dredging stuff up way up from high school, but what is the domain of the inverse tangent function? Yes, it's actually negative pi over 2 to pi over 2. So the inverse tangent is actually only defined from here to here. So if you're expecting it to give you report an angle in this range, it's not going to do it. So this is why I just like to take all of my angles off of the nearest x-axis and then just report the answer as such. It avoids all the trouble with the domain of the pesky inverse tangent function. I just bypass it entirely. I don't have to worry about it. But anyway. So it's the most reliable method, I believe. All right, other questions? Okay, have one more example problem I'd like to work through, and then we'll get out of here a little early. So let us consider this. This is problem 2.26, also from the Beer Vector Mechanics book. And let me find what page this is on. 34? Thank you. On page 34. So, let's see. Okay. So cable AC exerts on beam AB a force P directed along line AC. Knowing that P must have a 350-pound vertical component, determine A, the magnitude of force P, and B, its horizontal component. So, now this kind of thing actually looks a lot like a moment problem, which we'll see much later. Well, actually not much later, but probably next week. When I have my reference as a regular semester, so I'm thinking, oh, that's a ways off. I'm like, no, that's like next week. So anyway. Or possibly even Thursday. I'll have to consult the calendar. But yeah, so again, this is a very accelerated course. Please work on this homework tonight, if at all possible. In a normal semester, you can put off a homework a day or two, or even till the weekend or whatever. If you try to do that in this class, you're going to have a very hard time. So just try to keep that in mind. I know it's difficult, especially if you have work commitments and family commitments. I realize that's a very tall order. Most of you are working in some capacity if you're anything like the usual college students I see. So I realize that's a burden, but it's a 5-week course. It's just the nature of the beast. So here, this actually looks a lot like, as I was saying, this looks a lot like a moment balancing problem that we'll see later in the course. But for here, we're actually just looking at a simple Cartesian force problem. So what I'm really going to look at is I'm going to look at joint A here. Eventually, I'm going to actually formally introduce what a free body diagram is, and we'll talk about what that means. But for now, I'm just going to draw a force P at joint A. So I have this force here. It can't be. It's supporting the beam. It's a tension force. Yes, exactly. It can't be It can't be going downward. It's what's holding the beam up. See, this is a pin support here. If this thing were not a vertical force here, this whole thing would just flop on over, just either under the force from Q or from the self weight of the beam. Well, assuming the beam stops there, I can't really tell if the beam stops there or yeah, it actually looks like it kind of stops there. That doesn't look like a cut line. Okay, so knowing that P must have a 350-pound vertical component, determine the magnitude of force P and the horizontal component. All right, so this one's actually fairly straightforward. So I have this force P here, and I'm going to look at its components. Now, I know that I can see this 55-degree force, or this 55-degree here. Now, but the thing is that doesn't necessarily help, because what I really want is, if I'm drawing this thing from joint A, what I really want is this angle here. So what I'm going to do is I'm going to draw a little triangle here, and I realize this is a right triangle. So if this is 55 degrees, by simple logic, this has to equal, dang it, 35 degrees. Sorry, this is a bit of a learning curve on this thing. 35 degrees. It keeps thinking I'm trying to make a gesture. Okay, 35 degrees. This angle here has to be 35 degrees. So this is 35 degrees. And this is px. And this is py. Now, they say that P must have a 350-pound vertical component. That looks terrible. Yeah, so Py has to be equal to 350. So a 350-pound vertical component. That's important. So in other words, Py is equal to 350 pounds. Py is equal to 350 pounds. Next, so Py is equal to 350 pounds. And so now we can simply apply this logic. So now we can simply apply this knowledge and what we've learned. So in the previous problem, we had our original force and we were getting our components. In this, we have a component and we're trying to go backwards and get the original force. This is to just try to illustrate that you can go that these relationships work in either direction. So I know that Py is going to be equal to P cosine of 30, P sine. Helps if I write the trig, or it helps if I write the correct trig ratio. Py is equal to P sine of 35 degrees. P sine of 35 degrees, I know that because this angle is off of the x-axis. So therefore, P must be equal to Py over the sine of 35 degrees. Or 350 pounds over the sine of 35 degrees. So 350 over sine of 35. And this comes to 610.2 newtons. Oh, pounds. What's a unit among friends? £610.2 pounds. So we have the answer to part A here. This is the answer to part A. And now, so this is A, essentially. And then B is asking for the horizontal component. So Px is simply going to be P, times the cosine of 35 degrees. So that is 610.2 times the cosine of 35 degrees. And that comes to 499.9 newtons, or pounds. I'm stuck in Newton mode today. Pounds. And that is part B here. Okay, so that's the answer for part B, and that's how you handle that. Now, question, what if I wanted to get Px without solving for Py? Or sorry, what if I wanted to get Px without solving for P first? I could actually do that. An alternate way An alternate way is I could use the relationship. Okay, look, I have this triangle here. I realize this is a triangle. P, Px, Py. I could use the relationship, the tangent of 35 degrees is going to be equal to Py over Px. And work through the math, I will get that Px is equal to Py over the tan of 35 degrees, which would equal 610, or actually 350. Uh, 350 over the tan of 35, which will come to 499.9 pounds. Not newtons, pounds. All right, and that should do it. So, any questions on what vectors are, on how to work, on how to break them into components, and how to add them, their properties, and anything we've looked at so far today? Okay, you have your homework problems for today, so please try to work through those for tonight. I will see you tomorrow. We'll go over some homework problems, go over some new things. We'll be looking at three-dimensional vectors, and that'll work. I'll see you tomorrow, and as always, thank you.